মর্নিং, সুপ্রভাত, শুভ দিন। কেমন আছেন আপনারা সবাই? How are you all doing? Hope you are doing great today. So today we are going to talk about central limit theorem. Are we always confused about what central limit theorem really means? Why it is called central limit? Why is the word limit? Why it is central? And what is the central limit theorem all about? So in this video, I will express or explain in clear steps what is central limit theorem all about, and how then I will show you how we can practically apply it in a situation. So without further ado, let me rotate the camera and face the board. Okay. So today, as I said, central limit theorem. Have you ever always thought what is central limit theorem all about? Why it is called central? Why is the word limit used? And where exactly is it applied? So I will explain it in clear, easy steps what it means, and then I will show you how you can practically apply it to solve a practical problem. Okay, so so let's do the formal description. Suppose x1, x2, this comma, dash 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 xn is a sequence of independent and identically distributed. This is, we are talking about the probability distribution of x1 through xn. Okay, distributed random variables. That means these variables can take any value, such as a person's height, weight, etc. Random variable with expected value. Now expected value means mean, the center of the distribution, with expected value e of x, exi actually, where I is 1 through n. That is, the expected value is equal to mu, and variance, which you know is the square of standard deviation, is square of average deviation of a number from the center. And variance, which is given by variance xi, again I will assume value from 1 through n, is equal to sigma square. This is to be read as sigma square, which is small s in Greek language, ys because it's standard deviation, and again standard deviation is an average deviation of a number in the distribution from the mean. Okay. Where variance sigma square is less than infinity. Okay, and then as n approaches infinity, let's say the sample size approaches infinity, the random variable square root of n times the mean of the sample xn bar, Remember, this is the mean, this is the bar. And how far it is located away from the population mean times the square root of the sample size. Converge converge in distribution to a normal distribution. Okay, with mean 0 and variance sigma square. Okay, or square root of n times sample mean minus the population mean approaches a normal distribution. N means normal, mean is 0, sigma square is the variance. Okay, so your mean is 0 and variance is sigma square. So basically we are saying as the sample size becomes very large, then square root of n times the mean of the sample minus the mean of the population, that is how far the sample mean is away from the population, the deviation of the sample mean from the population mean times multiplied by square root of the sample size, converge to a normal distribution with a mean of 0 and variance of sigma square. Okay, so this is the formal description. How do we apply the central limit theorem in real life? So practical something that we can use in daily life is let x bar be the mean of a large, that is n is greater or equal to 30 simple random sample. Random sample from a population with mean or average mu and standard deviation, I'll write for short form STD, and standard deviation, again short form sigma. Okay, then x bar has an approximately okay normal distribution. That means bell-shaped distribution with mean mu x bar equal to mu, that is the mean of the sampling distribution is equal to x bar, and standard deviation which is given by sigma x bar. This is the probability distribution of the sample means. Each standard deviation is equal to standard deviation of the population divided by square root of the sample size. Okay, so probability distribution of sample means or X bar is called the sampling distribution, because the sample means are obtained from different samples from the population, is called sampling distribution. Sampling distribution. So you'll frequently see the use of the word sampling distribution in textbooks and course material. Its mean, the sampling distribution, its mean is mu x bar, the sampling distribution where the center, where the peak is the highest. It's a bell-shaped distribution. Its center is equal to the mean of the population, and sigma x bar, the standard deviation or an average deviation from the mean of the distribution, is equal to mean of the standard deviation of the population divided by square root of n. So this is sigma divided by square root of n. So this is the practical application of central limit theorem. What we learned here, that let x bar be the mean of a large simple random sample drawn from a population with mean mu and standard deviation sigma. Then the probability distribution of x bar, which is called sampling distribution. Probability distribution of sample means is called sampling distribution. Its mean mu x bar is equal to mean of the population, and sigma x bar, which is the standard deviation of the sampling distribution, is equal to sigma divided by square root of n. Now this standard deviation of the sampling distribution is also sometimes called standard error of the mean. Okay, so there you go. This is the practical application of the central limit theorem. Remember, we are dealing with the sampling distribution or probability distribution of x bar, which is bell-shaped with x bar on the horizontal axis. Relative frequency or probability on the vertical axis is bell-shaped. Its peak, where the relative frequency is the highest, probability is highest. On the horizontal axis is the center, mu x bar equal to mu, mean of the population, and sigma x bar, the standard deviation of this sampling distribution, is equal to sigma divided by square root of n, which is also called standard error of the mean. So let's work on a practical problem applying the central limit theorem. And I'll work on the other side of the board, and I will use my calculator TI-84. So if you have a TI-84, you can work with me. Okay, so let's go to the other side of the board. Okay, so here you go. Let's work with a different color pen. So this is the problem, practical problem. Problem on application. So if you have any doubt on how to apply the central limit theorem for sample means, here you go, on application of central limit theorem. Okay. So a serial manufacturer claims that the weight of a box of cereal labeled as weighing 12 ounces. Has a mean of 12 ounce and a standard deviation of 0.1 ounce. Okay, and a standard deviation of 0.1 ounce. Okay, you sample 75 cereal boxes. Okay, and weigh them. Let x bar, this is to be read as x bar, which is sample mean. Let x bar denote the mean weight of 75 boxes. Okay. A, part A. If the manufacturer's claim is true, claim is true, then what is the value of probability of x bar greater or less equal to 11.9? This is at most. Sample mean weight is at most 11.99. So part B, based on the manufacturer's claim, based on the answer for two parties, based on the answer to part A, part A. Okay. If the claim is true, then is 11.99 ounce is an unusual mean weight for a sample of 75 boxes, for a sample of 75 boxes. If the mean weight of the boxes were 11.99 ounce, would you conclude that the manufacturer's claim is false? Manufacturer's claim is false. Claim is false. Okay. So we will apply the central limit theorem. We will do the sampling distribution of x bar. Sampling distribution of sample mean weights of x bar, sample mean weights. So as we discussed, the central limit theorem states that for a large sample size n greater or equal to 30, the sampling distribution of x bar is bell-shaped and the peak, okay, where the relative frequency or probability is highest, okay. So you have x bar on the horizontal axis, you have probability on the vertical axis, so it's a probability density curve, okay, and the mean of this by central limit theorem, mu x bar equal to mu, and the standard deviation of the sampling distribution sigma x bar is sigma divided by square root of n. Now manufacturer claims that the mean is 12, okay, and then the standard deviation of the sampling distribution, standard deviation of the population is 0.1 divided by square root of 75. So you can use your calculator TI-84 to find 0.1 divided by square root of 75. So what will you do in your calculator? You will type 0.1 divided by, press the second button on the top left corner and then the excess square key in the first column halfway down. That gives you the square root. Inside the square root you are going to type the sample size, which is 75, and hit enter. So the standard deviation of the sampling distribution is 0.0115, you might say. Okay. Now you want to find out what is the probability for part A, x bar less than equal to 11.99. The center is 12, so 11.99 will be on the left of the mean, which is 12, and we want to find the area to the left of 11.99 under the sampling distribution curve. So probability x bar less than 11.99. Again, use your TI-84 calculator. Second button, then verse button. Verse button is in the third row. Then select number 2, which is normal CDF. This function will find the cumulative area. C stands for cumulative. Normal cumulative distribution function, probability density function. So cumulative area, my lower is a very large number or very high negative number on the left, which in the calculator will be indicated by -1 E99. E stands for exponent, that is 10 to the power of 99. So for lower, I will first type minus sign next to the enter button, then type letter 1, then I will press the second button again and comma button. Where is the comma button? On top of the 7 button. That will give us the capital E, small capital E99. So what does this really mean? It means minus, negative on the left, 1 followed by 99 zeros, 10 exponent 99. Very large negative number or very small negative number, as you may think. Upper is where we want to stop, is we want probability up until 11.99. The mean is 12, and the standard deviation is the standard deviation of the sampling distribution, which is 0.0115. Okay, so let's do the calculation. second, then verse button on the third row, then number 2 is normal CDF, then minus sign next to the enter, minus 1, then second button, and comma button on top of the 7 button gives me the E99. My upper is where I stop my calculation is 11.99. Remember, I want the area to the left of minus 11.99 under the normal curve, sampling distribution curve. So I start from negative infinity up until minus 11.99, my upper boundary. My mean is 12, and my standard deviation is standard deviation of the sampling distribution, which is 0.0115. And then I go down to paste and hit enter twice. This is important. Bring your cursor of the black rectangle on paste and hit enter twice. And the area is, so this probability is 0.1922. So there is a 19% chance that the sample mean is less than equal to 11.99. Okay. So part B based on answer is, then is 11.99 an unusual mean weight for a sample of, well, there's a 19% chance that the sample mean weight is less than equal to 11.99. 19% chance comes from this, the probability or the area under the sampling curve below 11.99. So is it an unusual mean weight? And not exactly. I mean, it's greater than 0.05. So part B, probability of X bar less than equal to 11.99 is equal to 0.19, which is greater than 5%. So X bar less than equal to 11.99 is not unusual. Any probability with less than 0.05, any probability of any event less than 0.05 will be unusual. In this case, probability is 0.19, which is greater than 5%. This is not unusual. Okay. So there is a 19% chance that the probability or the mean weight of 75 sample boxes less equal to 11.99, which is not unusual because the probability of this event, that is the mean sample weight less than 11.99, is greater than 0.05. That being the case, there will be occasions when you will draw 75 boxes from the population and weigh all the 75 boxes, divide by 75, add the 75 weights, divide by 75, you will find the probability of that event is less equal to 11.99 is 0.19. That means there will be occasions when the mean weight of the 75 boxes will be equal to 11.99 or less than 11.99. So answer to part C. Would you conclude the manufacturer's claim is false? Part C is yes. Why am I saying yes? Because there is a 19% chance that the mean weight of 75 boxes is less equal to 11.99, which is less than 12 ounces. So the manufacturer is claiming that the mean is 12 ounces and the standard deviation is 0.1 ounce, but there will be occasions when you draw a sample of 75 boxes, its mean weight will be less equal to 11.99 and its probability is not unusual. It is greater than 0.05. So that means the manufacturer should change his or her claim and say it cannot be 12 ounce, it has to be 11.99 or something like that. It is definitely less than 12 ounce. So this claim is incorrect. Okay, So answer to part C is manufacturer's claim, I would say, is unusual, is false. Yes. Okay. So I stop here today. If you like this video, give me thumbs up. I really appreciate that. Okay. And if you like this video, share with your friends. And please write me a comment if you like this video. I really appreciate that. And then please let me know where you are watching from. Okay. So let me rotate my camera. আপনাদের যদি এই ভিডিওটা ভালো লাগে আমাকে একটা থামস আপ দিন। আমি খুবই মোটিভেটেড হব যদি আপনারা আমায় থামস আপ দেন, এবং যদি আপনাদের ভিডিওটা ভালো লাগে আপনাদের বন্ধুদের সঙ্গে শেয়ার করুন, এবং প্লিজ সাবস্ক্রাইব টু মাই চ্যানেল বাই হিটিং দ্য red subscribe button on the bottom right corner, and please do not forget to click on the bell button which will notify you every time I upload a new video, which I do quite often. Okay, and again, please do not forget to watch me tomorrow when I'll be back with another new video. Okay, ইনশাল্লাহ আবার দেখা হবে কালকে। ভুলবেন না চ্যানেলটা চেক আউট করতে। থ্যাংকস ফর ওয়াচিং, অ্যান্ড ইফ ইউ হ্যাভ এনি কোয়েশ্চেন রাইট মি আ নোট। কোথা থেকে ভিডিওটা ওয়াচ করছেন সেটাও জানাবেন। আমি জানতে চাই, আমি খুবই উদ্গ্রীব যে আপনারা কোথা থেকে আমার ভিডিওটা ওয়াচ করছেন, কেমন লাগছে ভিডিও, আরও নতুন কিছু পড়াবো জানাবেন। হ্যাঁ, so if you have any interest in any other subject or in any other math problem, let me know. You can write me a note on the comment section and I'll respond to each one of you. Thanks for watching. Take care. Have a nice day, and please do not forget to watch me tomorrow. Take care. Have a nice day.